Good morning, sir. Good afternoon. Sir, you are host now. Sir, am I audible?
Yes, ma'am. Am I audible to you?
Yes,
Madam?
sir. Recording is recording is on.
Hello.
And host now. Yes, you are audible.
Is any setting I have to do over here? Hello.
No, sir. No. Nothing to be done.
Then at the end, yeah, whether that will ask me whether to save that one.
No, nothing. It will not ask you anything today. You can
Okay.
just leave.
Okay. And then automatically it will get saved.
Yes, you can end the meeting.
Okay. Okay. I will do that.
Okay.
Yeah.
Okay.
Good afternoon, Suresh sir.
Good afternoon.
Yes. Am I audible?
Yes.
Yes, sir. Thank you.
Actually, I think
Yes, sir. Sir.
Sir has not joined.
Who?
Um, who is taking lecture today?
Uh, actually, I am on the other side right now today.
Acha.
Yes, sir.
Are you conducting the lecture today?
Yes.
Okay. I think we have 5, 6 participants, but no one has joined, no? Okay.
Yes, we are 4 5 persons.
Yeah.
Sir, shall we start?
Yes, I think we can start.
Yes, sir. Good afternoon, all of you. Today is my opposite desk presentation. Even though I am the participant of like you, I already taken this course for the BE graduate students. That is also named as Energy Audit and Management. But currently, I'm just studying in depth with the help of you all. So whenever if you feel that I'm getting on wrong or anything you want to add, so that can be helpful for me as well, you can add, no issue. My name is Dr. Amar Singh Kansepatil. I completed my BE Mechanical, ME Mechanical, and PhD from IIT Roorkee. My area of expertise is renewable energy systems. And in engineering college, from last 15 years, I'm working as an associate professor in Department of Mechanical Engineering. Now, today's our lecture is related to the fans and blowers, which is the book number 3, chapter 5. In this chapter, we are going to discuss the fan types and its applications, the fan characteristics, curves, performance curves, what are the fan laws considered for this performance, then the fan efficiency and its factors which are affecting, few design and selection criteria. Then major thing which will affect for the fan is the pressure drop and its resistance, which is known as system resistance. Then we have to discuss the flow control strategies, then the performance assessment, and at the last, we are going to discuss what are the saving opportunities for the fans and blowers. So that is the main thing which we are going to discuss at the end. Now, when we start with the fans and blowers, they are classified in 3 categories. One is the fans, another is the blowers, and third one is the compressors, which will provide the air for ventilation and industrial process requirements. Their function is to pressurize the air or gas, and they have to move it, force it to move the gases and air against the resistance. The resistance which is caused by ducts, dampers, and other equipments. As we have discussed the fluid mechanics in our engineering days, there is a resistance for the fluid. The same resistance is applied to this airflow as well. This resistance is overcome by the rotor, fan rotor, which will consuming the electric, which is consuming the electricity. So that will be transferred to the rotating shaft and the motor. Now, how you can differentiate the fans, blowers, and compressors? These 3 are considered with the help of a specific ratio. Now, what is meant by specific ratio? The specific ratio is the ratio of the discharge pressure over the suction pressure. Discharge pressure over the suction pressure. And this specific ratio is different for all these components. That is fans, blowers, and compressors. For fans, it is up to 1.11. For blowers, it is 1.11 to 1.2. And for the compressors, it is more than 1.2. When we see the 3 components of these fans and blowers, the fans are used mainly for the high discharge and low pressures. So if you can see, the pressure rise is 1136 mm of water columns or gas. Then if you go with a moderate pressure and moderate discharge, then we have to go for the blowers, where the specific ratio lies between 1.11 to 1.2, and the pressure rise is 1136 to 2066. But for the as compared to the fans and blowers, small capacity but high pressure, we have to move to the compressors. Now, again, there are the different types of fans which are considered. If you can see the table 5.2, they have mentioned the different types of fans and their efficiency. The fans and blowers, their selection are depends on the volume flow rate, pressure, and the volume flow rate, pressure. Try to highlight it. The volume flow rate, pressure, and types of materials handled. Also, we have to consider the space limitations and the efficiency. So the different efficiencies are mentioned over there. The airfoil and uh, background backward curve inclinations.
It's a Jyoti, it's a Rama.
Yes, sir. Yes, sir. Okay. So the efficiency for this airfoil and backward curve is curved or inclined centrifugal fans has the highest one, that is 79 to 83%. And then the efficiency slightly goes on decreasing for the modified radial, then pressure blower, then forward curves. In axial fan, which is the differentiate between two fans, that is a centrifugal fan and axial fan. The Vena axial fans have the highest efficiencies, that is 78 to 85. Then tube axial, which is having 67 to 76, and the propellers are also have the efficiency in between 45 to 50. That is the half of the actual power consumed by them. In this one, uh, we have to see that the backward curve or inclined propellers have shows the highest efficiency whenever we design for the fans. Now, when we shift, so yes, now these are the centrifugal fans and axial fans, as you have already aware about that one, which are the belt driven or directly motor coupled. This is the directly motor coupled. This is the motor, and this is the belt driven. So which will shows over here. Now, again in centrifugal types, they have classified as radial fans. This is the radial fan. This is the radial. This is the radial fan. Okay. The most of the industrial workhouses are concentrated on this radial fans for this high static pressure, which is up to the 1400 mm of water column, and the ability to handle the heavily contaminated air streams. But they have the good simple design radial fans, which are well suited for the high temperatures and medium blade tip speeds. The second one, which is considered, is the forward curve. So this is the radial blade. Second one is the forward curve. Now, the forward curve uses the clean environment and operates on the lower temperatures. They are well suited for the low tip speed and high airfoil work. Which they are suited for the high speed and high airfoil work. Third one is the backward or inclined fins, which are the considered to be the most suitable or more efficient than that of the forward curve fans, which will be reaches the peak power consumption, and then the power demand drops off well within the usable airflow range. These backward inclined fans are known as non-overloading fans. This is the third one, is the non-overloading fans. Third one is the non-overloading fans of the. So these are the three types in the centrifugal fans. Now, next point is the axial flow fans. Here, the axial flow fans are shown over here. First one is the tube axial, where the fans are kept inside the tubes and mostly they are coupled with the motors. Okay. Second one, the tube axials, which kept in the cylindrical housing, okay, and which have a very close clearance between the blade and housing, which will improve the airflow efficiency. This fans run faster than the propeller fans, which will be the operational for the higher pressures of 250 to 450 mm of water column, and their efficiency lies between 65%. Next is the vane axial. Now this vane axial, the vanes are guided to the incoming airs. These are also kept inside the cylindrical portions, but with a guided vanes or guide vanes, which will improve the efficiency and which will use a direction to the flow. They also have the high static pressure with less dependence on the duct static pressure. Such fans are used generally for the pressure up to 500 mm of water column, which are more energy efficient fans available and should be used whenever possible. So whenever we will recommend, we have to recommend the vane axial fans. Third is the propeller type. The propeller fans runs with a low speed and moderate temperature. They experience a large change in airflow with a small changes in static pressure. They handles large volume of air at low pressure and at low rigidity. They are often used indoors as exhaust fans. The outdoor applications, which includes the cooled condensers and cooling towers. Their efficiency is as low as approximately 50% or less. So these are the three which comes under the axial flow types of fans or radial fans, and these are the three which comes under the centrifugal fans. Now the next point, which is common blower types. Now the blowers which can achieve a much higher pressure than the fans. In one book where I have taken one unit, that is fans, blowers, design of fans, blowers and compressor, they have mentioned that the for the higher pressures, if you go with the blowers, they are achieve a much higher pressures than that fans, which has 1.2 kg per centimeter square. Now they are used the negative pressures for the industrial vacuum systems as well. Their major types are centrifugal blower and positive displacement blowers. Now when we go with the centrifugal blowers, they are working as like the centrifugal pumps. The impeller is typically driven and rotates as fast as 15,000 rpm. In multi-stage blowers, the air is accelerated as it passes through each impeller, and a single stage blower, the air does not take many turns, hence it is more efficient. They will typically operate the pressure from 0.35 to 0.7 kg per centimeter square, but can achieve the higher pressures. If you see the characteristics curves of these blowers, that airflow tends to drop drastically as the system pressure increases. And this is the biggest disadvantages in material conveying systems that depends on the steady air volume. And because of this, they are most often used in applications that are not prone to clogging. So that is the things we have to consider for this centrifugal blowers. Now this will give us a typical differentiation for the centrifugal fans and axial flow blowers. Among them, the three types where we can use all the three types. If you go with a radial centrifugal fans, the high pressure and medium flow is considered. If you go with the efficient close to the tube axial fans and power increases continuously are the characteristics of radial fan. Their typical applications are various industrial applications suitable for the duct-laden and most moist air and gases. Now, if you go with a forward curve blades, then medium pressure to high flow, deep in pressure curves, their efficiency is higher than the radial fans and power rises continuously. These are the characteristics. Among them, the power rises continuously is the drawback of this forward curved plates. So their typical applications are low pressure HVAC systems, packaged units, which are suitable for the clean and dust ladder air gases. The more efficient is the backward curved blades. They will give the high pressure, high flow, and high efficiency. The power reduces as flow increases beyond the point of highest efficiency. So when we keep this high efficiency more than that of their highest, then the power consumption will be decreased. The HVAC, various industrial applications, and forced draft fans are the main applications of this backward curved blade. Last is the airfoil type, same as the backward curved types, which have highest efficiencies, which will be used for the different applications, HVAC, various industrial applications. But the axial flow type of blades are required clean air. So the whatever application industry we can take, the air or gas should be the clean. We will go with the axial flow fans. Then again, three types are there: propeller, tube axial, or vane axial. If you go with a propeller, they have a low pressure, high flow, which gives them low efficiency. The peak efficiency close to the point of free air delivery pad. That is the zero static pressure. So they are used for the air circulation, ventilation, and exhaust. Second one is the tube axial, which will give the medium pressure, high flow, high efficiency than the propeller type. They are deep in pressure flow curve before the peak pressure point. Their applications are HVAC, drying ovens, exhaust systems. The most efficient, that is the vane axial, which will give the high pressure, medium flow, then deep in pressure flow curve, which will use of guide vanes improves the efficiency. The high pressure applications, including the HVAC systems and exhaust. So these are the applications for the different different axial pumps and the centrifugal pumps. They have mentioned that the positive displacement blowers have rotors which will trap the air and push it through housing. So the positive displacement blowers provides a constant volume of air even if the system pressure varies. However, so they are suitable for application prone to the clogging. Okay, since they can be produced enough pressure, typically up to 1.25 kg per centimeters, and they turn much slower than the centrifugal blowers. That is, the centrifugal blowers RPM is 3600 and are often belt driven to facilitate speed changes. Now, whenever we consider the fan performance, their evaluation and efficient system operation, some characteristics we have to consider. First is the system characteristic. Now, whenever we say the system characteristics, the first term come into mind is the system resistance, which is used for when referring to the static pressure. The system resistance is the sum of static pressure losses in the system. There's different static pressure losses are there. So bends are there, narrow passages are there, like that. Then the system resistance is a function of configuration of ducts, pickups, elbows, and the pressure drop across the equipment. For example, back filters, cyclone, etc. Now, this curve, that is figure 5.5, shows the system characteristics. On its x-axis, there is the airflow rate, which is shown 0, 1x, 2x, 3x, like that. And on the y-axis, it shows the total static pressure drop, which will grows +1, +2, +3, like that. So as the airflow increases, with the total static pressure drop in water column also increases. Now here we have to note that the system resistance, which varies with the square of the volume of air flowing through this system. So whenever we consider any system resistance, its airflow matters a lot. So the resistance will increases is directly proportional to the square of the volume of the air. Now, in this one, the conversely, the resistance decreases as flow decreases. So to determine that volume the fan will produce, it is therefore necessary to know the system resistance characteristics. So in existing systems, the system resistance can be measured. However, for the designed systems, specifically designed systems, we have to calculate the system's resistance. Now, the next point is related to the fan characteristics. The fan characteristics represent in the form of fan curves. The fan curves are the performance curves for a particular fan under a specific set of conditions. The fan curves will gives us an idea about the fan volume, system static pressure, fan speed, the brake horsepower required to drive the fan under the static conditions. So some fan curves will also include the efficiency curves so that the system designer will know that where on that curve the fan will operate under the chosen conditions. So that they have shown the figure 5.6. So this is the fan characteristics curves. Sorry. Yes. So the first one is the static pressure curve, which will goes down over there. Okay. And the next one is the HP breakage horsepower or Then the static efficiency one, which will come on the spot as the highest efficiency. Then the systems curve, which will goes on increases with the static pressure in WG, and CFC. CFC is the cubic feet per minute. Cubic feet per minute. Then this will be the different curves which are considered for the fan characteristics. The fan characteristic curves where the static pressure, that is SP versus flow, is especially very much important for the consideration. So this will be the very much important for the consideration. The intersection of the system curve, the system curve varies on this side, and the static pressure curve, this one, and this one will be the intersection. The intersection of the static curve and the static pressure curve defines the operating curve. So this is the main point which we have to consider while selecting the fans or blowers for the different applications or replacing the existing fans. Now the pressure which is required by the system over a range of flow can be determined by the system performance curve, and these are the different system performance curves which are shown in front of you. In this, the fan which actually operates the fan's actual operating point now the next curve, when only we consider these two curves, the next diagram will shows how we are going to operate these curves. Suppose N1 is the speed, okay, and this is the what can say static pressure curve, which will come from this one, okay. This will be static pressure curve, and the system curve, which is shown on the dotted line, that is the SC1, which will intersect at point A. Now, when it intersect at point A, the discharge at that point is the Q1, and the pressure at that point is P. Now, my aim is to reduce this consumption, okay. So I have two methods or two options to reduce that one. Which are they? Either I have to reduce the speed. So instead of going for the N1, I have to go for the N2. So when I just reduce the speed, the second fan curve or static curve, a static pressure curve will be shown over there, which intersect this SC1 at point C1. So this will be our Q2. So automatically the speed will reduces, the discharge will reduces. However, the power also get reduces. So this will be the first method. Instead of reducing the speed, if we keep the speed as it is, that is this N1 as it is, N1 as it is, okay. We have to go to the point B. We have to go for the point B. How? We have to change the system curves. We have to change the systems curves. That the system curves, okay. We have to restrict the flow going out after that. That is restrict the airflow by partially clogging the dampers in the system, which will reduces the flow. This is transfer from Q1 to Q1. And our second system curves will be appearing over here, but the pressure remains at P2. So if you restrict the flow, the pressure increases. Okay. If you reduces the speed, the discharge as well as the pressure both will get reduces. So these are the system characteristics and fan characteristics shown over in this figure 5.7. So the reducing the fan speed is much more efficient method to decrease the airflow since less power is required and less energy is consumed. So this will be the shows in our diagram 5.7, the pressure versus system curve, pressure versus airflow. Now the three fan laws are considered or used. Three fan laws are used first is the flow versus speed. Second is the pressure versus speed square, or and third, the power versus speed cube of speed. So the fan which operates under a particular set of laws, considering speed, power, and pressure. So when the flow versus speed, if you can draw, it becomes a straight line. That is, flow is directly proportional to the speed. So Q1 upon Q2 is equal to N1 upon N2. So when you reduces the speed, automatically the discharge will be reduces. But what will be the effect of this reduction in speed? Here they have mentioned, if you vary the RPM by 10%, either you decrease or increase the RPM, then the air delivery will be decreased with 10%. So this first law, that is flow versus speed, will shows us that same amount of energy, same amount of airflow delivery will be reduces. However, when we go with the speed, the pressure is directly proportional to the speed square. If we reduce the RPM by 10%, then the static pressure will be reduced by 19%. The static pressure will be reduced by the 19%. And the RPM, if we reduced by 10%, then the static pressure will be, if your RPM increased by 10%, the static pressure increases by 21%. So this will be the second law, that pressure versus speed. Pressure is directly proportional to speed square. The third one is the power versus speed. Kilowatt, the power, and N is the speed, RPM. So it indicates that if we reduce the RPM by 10%, if you reduce the RPM by 10%, then the power requirement decreases by 27%. However, if you increase the RPM by 10%, the power consumption increases by 33%. So these are the questions I think they will ask for the your MCQs, multi-choice questions. There are some numericals also over there, where we require these equations or formulas. Now the next point, which is related to the fan design and selection criteria. We have to precisely determine the airflow and the required output pressure, which are the most important in proper selection of fan type and their size. So to find out that one, again, a big challenge for us that we have to consider the heat transfer rates or combustion air or flue gases quantity which we have to handle. So these points we have to consider for the handling of this thing: heat transfer rate, combustion of air and flue gas quantity which we have to handle. The system pressure, which pressure requirement is usually more difficult to compute and predict. So these things which we have to consider with a pressure drop should be added to the fixed pressure requirements of the process. The pressure drops, as we know, that are because of the bends, the friction between the fluid and the duct, or you can say fluid and the duct surface, then cross-sectional areas, different cross-sectional areas. So that pressure drop we have to consider in this one, especially the case of ventilation fans. There is no fixed pressure requirements, so variable pressure drops are observed on that. So a very comprehensive approach, so very conservative approach we have to adopt, allocating the large safety margins, which will resulting in oversized fans, and that oversized fans will increase the uh, energy consumption. So we have to avoid that one, and which operate at a flow rate much below than the design value, and consequently they will step into the poor performance. So we have to go with a system flow and pressure requirement, and that we have to determine. So once we have determined it, then the fan and impeller types we have to select. The best results will be added when the value should be obtained from the manufacturers of the specific fan and impeller. So the manufacturer's catalog will give us the best uh, selection parameters for the selecting the fans. Now the choice of the fans and the types for the given application depends on the magnitude of required flows and static pressure. For a given fan type, the selection of the appropriate impeller depends additionally on the rational speed. Here, the high speed small units are generally more economical because of their high hydraulic efficiency and relatively low cost. However, if you go with a low pressure ratios and large and low speed units, they are most preferable. The next point is related with a fan performance and its efficiency. So, sorry. Now here, the three pumps or fans, sorry, not pumps, three fans are shown over there. The dotted lines are for the forward curves. This is the dotted line, which is for the forward curve. Okay. Then the continuous dotted line is required for the radial curves, considered for the radial curves, and continuous line is for the backward curves. Now, these are the static pressures. Okay. Same way, they will have a static curves as well. Sorry, system curves as well. So this is the system curve for forward. This is the system curve. This is the system curve for the radial, and this is the system curve for the backward curve pumps. Now, in these curves, what we gain or what the performance and efficiency gain we have, the typical static pressures and power requirements, we are counting it because they're intersection points. Like suppose this one is the intersection point of forward curve. I will name it as A. Then this is the intersection point of radial curves. I name it as B. And this is the intersection point of backward curve, which I name is as a C. Okay. So in this case, we have to consider the fans, centrifugal special fans, the hub to tip ratio, that ratio of inner to outer diameter, outer impeller diameter, the tip angles, that is angle at which the forward and backward curved blades are considered, or that angle we have to consider. And the third one, the blade width, which determine the pressure developed in the fan. Here, we will see that the point A is the highest one, which has a forward curve fans have a large amount of hub to tip ratios compared to the backward one, that is A. If you compare with A to the C fans, which will produce the lower pressures. So these points we have to consider for the considering the fan performance and the efficiency. This is for the centrifugal things, the static pressure and power requirement for that one. So the power A, power B, and power C. So C will be the lowest one for the backward curves. So this curve shows that the backward curve centrifugal fans are more efficient, less power consuming than that of the other. Now, this figure again shows the efficiency, the curve efficiency against the flow rate. The highest efficiency which we have observed over here is for the airfoil, then that of the backward curve, then that of the radial, and then forward, and lastly the tabular. So the radial fans can be made with a different heel to tip ratios to produce different pressures. Both the design and off design points, the backward curves fans provide the most stable operations, and the most backward curve fans will decreases at the flow higher than that of the design values. This similar effect can be considered. This similar effect can be considered or obtained using the inlet guide vanes instead of replacing the impellers with a different tip angles. So radial fans are simple in construction and are preferable for the high pressure applications. The next point they have mentioned is the forward curves, which are less efficient and than that of the backward curves. Also, they mentions that they are more expensive to operate despite their lowest initial cost. Now, among the centrifugal design, which they have mentioned, among the sorry. No, yes. Now, among the centrifugal fan designs, The airfoil designs provide the highest efficiency, up to 10% higher than that of the backward blades, and use is limited to the clean and dust-free air. The airflow fans produce lower pressure than that of the centrifugal fans, but they exhibit a deep in pressure before reaching to the peak pressure points. Next, the propellable type fans are capable of high flow rates at lower pressures, while the tube axial fans have medium pressure and high flow capability and are not equipped with guide vanes. So these are some characteristics they have mentioned. Then vane axial fans, which are equipped with inlet and outlet guide vanes and are characterized by high pressure to medium flow rate capabilities. The most part which we have to discuss over here is the performance of these curves. Yes, performance of these curves. The performance is depends on the fan enclosure and duct design. So this will gives a performance. The spiral housing designs with inducers and diffusers are more efficient as compared to the square housings. Also, the density of the inlet air is another important considerations, since it is affect the both volume flow rate and capacity of the fan. So these are the system parameters which will affect it. First, system parameters which are affecting it. First is the design, spiral housing design. Okay. Second is the density of the air. Second is the density of the air. Third one is the inlet and outlet conditions. Inlet and outlet conditions with whirl and turbulence, which are created by grills and dampers. This is the third performance character which we have to consider or give a significant effect on the performance curves. Then the bends and elbows, which are at inlet and outlet of the ducting, which can change the velocity of the air and therefore the changing the fan characteristics. Their pressure drops in these elements is attributed to the system resistance, and it's all these parameters, that is enclosed and duct design, density of inlet air, inlet and outlet conditions, bends and elbows are known as system effect factors. These are known as system effect factors, and therefore we they have we have to carefully evaluate for the fan selection or modification of the fan, replacement of the fan. These are the most affecting system parameters for the fan performance curves. Now, the next point is related with the centrifugal fans, which are suitable for lower to moderate flow at high pressures, while the axial flows are suitable for the low to high flows at low pressures. The comparatively centrifugal fans are more expensive than the axial fans. Then, but the fan prices varies widely as they are based on the impeller types and mountings. So direct on belt coupled or wall or duct mounted, this will affect the fan prices. So in this parameter, the centrifugal fans and airfoil and backward curve blades design tends to the somewhat more expensive than that of the forward blade designs, but gives a more favorable economics on the life cycle basis. So if you consider their life, then the more favorable economics are provided by the backward curved blades, aerofoil, and centrifugal fans. But one point they have mentioned over here, that the reliable cost comparison are very difficult since the cost vary with the number of applications and application specific factor. But we have to choose the fans with the help of the technical and economic evaluation, which are with the available options by considering the minimum life cycle cost. The next point in this chapter they have mentioned, which are related with a safety margins. So safety margins are the another parameter which will affect the selection of the fans and floor. Now, the choice of the safety margin affects the efficient operation of the fan. They have mentioned over there, if you consider the boiler, then the industry fan can be designed with a safety of 20% on volume and 30% on the head basis, while the forced draft fans and primary air fans do not require any safety margin. However, the safety margins are already considered for them as at 10% of the volume and 20% of the pressure, which we have already considered. But this is for the specific conditions. If you go with a generalized one, the safety margin is almost 5% over the maximum requirement of the flow rate. So we have to consider the 5% safety margins for all the general application. However, 20% on volume and 30% for the head basis for the boiler, and for the forced draft and primary air, 10% by volume and 20% on the pressure head we have to consider. Now the next point, they have mentioned the fan specifications, some points which we have to consider for the fan specifications. Sir, am I audible?
Yes, yes.
Okay. If you want to add anything, you can please convey. No issue. Now, some specific points on the fan specification which we have to consider while either replacing the fans or specifically designing the fans. The first point they have mentioned, the design operating points of the fans should be volume and pressure. One. Then what will be the normal operating points is the volume and pressure. What is its continuous rating, maximum continuous rating? What will be its low load condition? They have marked over here that whenever we design, we are designing in on long-term basis. So when we select the fans, initially the few years, it may happen that we have to run that fans on lower capabilities. So the low load operations is the major parameter while considering the fans. On the latter stage, once the upgradation or expansion of the unit has been occurred, then that time the that time then they will go with a higher load operation requirements. So they have mentioned specifically that we have to take the manufacturer's consent for selecting for the both the conditions, that is initial low load conditions and the final high load conditions. The next parameter which they mentioned that is the ambient temperature, because as we know that the temperature also affects the density of the air, and as the density of the air affects, the volume flow rate definitely affects that one. So So this density of the gas, uh, we have considered the ambient temperature. Now the next is the density of the gas at different temperatures we have to consider for the fan outlet. Then composition of the gas. As we are handling the flue gases, we know that we have a water vapors, we have a CO2, where we have a CO and other gases as well. So that composition is very important while choosing the material of construction of the fan. Then dust concentration and nature of the dust, whether it is a bagasse dust or whether it is a cold hard dust, that we have to consider while selecting the or designing of the fan. So dust concentration is the major parameter for that one. Then the next is the uh, here they have mentioned that uh, the operating frequency is varies from plant to plant. So depending on the source of the power supply, we have to adjust that things. So since they are directly affect the speed of the fan, the frequency privilege or being maintained in the plant also needs to be specified for the supplier when it supplies the fans or blowers. Also, uh, the last point is the altitude of the plant, which we have to given to the manufacturer. So accordingly, they will suggest, or while we are choosing the plant, choosing the fan, we have to consider all these points. The choice of the speed of a fan can be best fit to the fan manufacturer. So they emphasize on this book that we have to give a chance or we have to take the opinion of the manufacturer for considering all these points for our applications. Now, the next point is related with system resistance and pressure drop. As all of us, we know that whenever there is a fluid flow, there is a resistance to the fluid flow, and that resistance will drops the pressure. Some applications require a specific pressure, some applications require a specific volume, and some applications require a specific temperature. But the most things which we are going to consider is the volume and pressure. So they have mentioned one diagram over here. Sorry. Yeah. This is the diagram which will gives us a pressure drop across the various equipments. They mentioned that the system resistance has a major role in the determination of performance and efficiency of a fan. So this system resistance are also depends on the processes. So to avoid the resistance, we have to apply the coatings or erosions of the linings inside the ducts. In some cases, the different equipments like replacement of multi-cyclones with ESP and installation of low pressure drop cyclones are more convenient. So we have to consider that options as well. Then we have to go for the duct modifications, then drastically shift the operating points, which will result in the lower efficiency. So we have to consider these points while considering the pressure drops. And this system resistance should be considered periodic. Now, this is the one case study that they have mentioned. We know that there is a boiler. Whenever there is a boiler, there is a fire, and the flue gases come out of the boilers. When that flue gases come out of the boiler, okay, if you measure the pressure, that pressure becomes the minus 10 mm of water column. When it enters to the economizer, which is the second equipment, again the pressure becomes, or pressure resistance becomes minus 30 mm of water column. Then we have to send that flue gases to the air preheater. Again there will be a resistance minus 40 mm of water column. After giving the heat in economizer as well as air heater, now we have to remove the suspended particles, that is called dust control system, where we have a resistance of 150 mm of water column. Then that dust will be removed. Then there will be ID fan whose own resistance becomes minus 230 mm of water column. Now this minus 230 mm of water column, how it comes? That is minus 10 plus minus 30 plus minus 40 and minus 150. So this addition becomes 230 mm of water column. It is not meter of water column, it is mm of water column. But not only that, ID fan has to suck the flue gases from all these equipments, that is from boiler, from economizer, from air heater, or the duct control. That ID fan also has to push that flue gases to the stack or chimney, and the resistance offered by or given by the stack is the plus 10 of mm of water column. Now how to calculate the total resistance? So for that they have mentioned over here. So here they have mentioned, if you want to calculate the total outlet and inlet pressure or total overall resistance, that is a pressure drop, we have to minus this one from minus the positive side from the minus of the suction side. So 10 minus of 230 becomes 240 plus 240 mm of Hg, and that is the total resistance which will be for the air or flue gases which the ID fan has to force. So this will be the resistance calculation for a resistance calculation or pressure drop calculation for a boiler flue gases which is coming out of the boiler. Now the next point in this, they have mentioned is a fan system curve. Now how to choose a particular fan for our system resistance curve? Now we have calculated the 240 mm of water column, that is our system curve, right? Now for that, the system curves we have drawn against the total pressure drops against the flow rate of flue gases. Now this curve will be system resistance curve for the different flow rates. Now we have to adjust a curve, that is system curve or static pressure curve, such that it will intersect at this operating point. And accordingly we have to choose the fan or centrifugal pump for our ID fan application, which is installed before the stack and after the precipitors. So they have mentioned over here that this operating point we have to choose. The system resistance is a function of gas density and velocity of the gas. After the boiler firing, it is started, and there is a continuous increase in generation of flue gases, and accordingly there is a continuous increase in the velocity of the gases and continuous increase in draft. When the boiler is fired at rated capacity, the generation of flue gases are maximum, resulting in corresponding pressure drop, which is the operating point. This is the operating point. So this operating point, we have to find out the curve, this dotted curve for this operating point, which passes through this operating point. So a characteristics or performance curve passing through the operating point of the system at the highest possible fan efficiency has to be selected for the better utilization of the energy. So what we have to do, we have to find out the operating point where the 250 mm of boiler is fired and this Q is be there. So that performance, we have to find out the which is the best suitable point which is near to this one. And among these points 1, 2, and 3, which will give the highest efficiency, that we have to find out, and that fan we have to select for the for ID fan. Now, few flow control strategies are also explained in this chapter. Okay, the flow control strategies, different flow control strategies they have considered over here. One is the pulley change, damper control, inlet guide vanes, variable speed drives. These are the different one. This flow control, why we have to go for the flow control? Because as we know that the fans are normally working on the steady or constant speeds. So the fans which are operates at a constant speeds. So their flow will be constant and their energy consumption will be constant. However, in some cases, there will be flow requirement, air or gas flow requirement will be vary. And that time, we have to reduce the energy consumption with the reducing the speed. So these occasions, the speed change is desirable, and adding a new run to the duct that requires an increase in airflow, that is volume, through the fan. So this instances the fan becomes oversized or flow reductions are occur in such situations. So the different things are considered: pulley change, damper control, inlet guide vanes control, speed variable drives, series and parallel operations. These are the few considered points for the flow control strategies. First is the pulley change. Now they have given a simple and good example over here. Just a minute. Yes, this one. Where they mentioned that suppose uh, two wheels are there, one it at 1 inch, 8 inch, and another will be connected pulley on of the 10 inch. Okay, one is connected to the motor, another is connected to the fan. The motor runs at RPM 1470 and the fan connected pulley runs at 1181 RPM. So if you consider the power consumed by this motor is almost 26 kilowatt. Now this pulley change system will says that we have to keep a parallel pulley which diameter is less. In second case, you can see that the diameter is less, that is 16 inch. When it's shifted to the 16-inch pulley, the RPM of the motor remains same, that is 1470 RPM. However, the RPM of the fan reduces, that is it becomes 882 RPM, 882 RPM. But this shift to the reduction in the power. That is, the power reduces to the 40 kilowatt. So they have mentioned over here, they have mentioned over here that the higher the size the fans operating with damper control was downsized by reducing the motor drive pulley size from 8-inch to 4-inch. The power reduction becomes 12 kilowatt. So this is the one of the method that will reduces the power consumption. Okay. Second method is the damper control. In damper control, the dampers are considered or used for inlet and outlet portions. The dampers will reduce the flow. However, it will increase the pressure. So the damper provides a means of changing the air volume by adding or removing the system resistance. This resistance forces the fan to move up and down along its characteristics curves and generating more or less air without changing the fan speed. But this will affect, or this will be limited amount of adjustment can be done. And they are not energy efficient because motor is consuming that much power continuously. Only we are controlling the flow. So they are not that much efficient. But however, we can control the flow with this one. Next is the inlet guide vanes. In inlet guide vanes, that guide vanes are the curved portion. The inlet guide vanes are the curved portions or curved sections that lay against the inlet of the fan when they are open. So the air which is entering inside the fan, we are guiding that air, okay, and they are closed guide vanes which will give a free swirl of the air entering the fan housing, and this changes the angle at which air is presented to the fan blades. So the air which enters to the fan has a particular directions. This will gives that guide vanes will gives the energy efficient for the modest flow range, which is considered from 100% flow to about 80% flow. They are most efficient, but below 80%, the energy efficiency of such type of equipments is dropped. So the inlet and outlet guide vanes will also control the energy efficiency, but they have their limitation approach. The axial flow fans can be equipped with variable pitch blades, which can be hydraulically or pneumatically controlled to change the blade pitch. The variable blade pitch modify the fan characteristics substantially and provides the dramatically higher energy efficiency than that of the other options discussed still now. Means other than that of the damper control and other than that of the pulley changeover. The next point is variable speed drive. So next point which we can control is the variable speed drive. The variable speed drive is efficient, however, they are most expensive. But they will give infinite variable speeds to control. So if you need N1, you can go for the N1. If you go for the N plus plus one, so the variable speeds can be achieved with variable speed drives. But this will reduce the speed of the fan and eventually the flow requirements. The fan performance can be predicted at different speeds using the fan laws. However, However, the power input to the fan changes as the cube of the flow. The power input of the fan changes is the flow of the cube. This will usually the most efficient from the control capacity control. However, few are the drawbacks of this system. They may not be economical for the systems. They require infrequent flow variations when they consider the variable speed drives and efficiency of the control system, that is fluid coupling, eddy currents, VFD, etc. And this should be accounted for the analysis of the power consumption when you consider the variable speed drives for the reduction of the fan speeds. Sir, I will take 1 minute. I will take water and then again I will start. Okay. Now we have discussed the three flow control strategies. The first one is the pulley change. Second one is the damper control. And third is the inlet guide vanes. And fourth one is the variable speed drives. Now, the next one, which commonly or most effectively can be considered by the industry, is the series and parallel operations. In series and parallel operations, we have to keep the same size or lower capacity fans in series or parallel combination. In parallel combination, all the 3, 4, whatever the fans we have used gives the airflow. So the volume will be multiplies on that proportion. And in series, the volume flow remains same. However, the pressure will be goes on increasing. In this figure 5.15, the series and parallel flow operations has been explained. Now, this dotted line will give the two fans in series, and this dotted line gives the two fans in parallel. When you keep the fans in series, the high resistance is occurs, and this will be the intersection point for them. While if you keep the parallel, the low resistance will occur, and this will be the intersection point or operating point for the parallel series. This will be for the single one, and these are for the two fans in parallel and two fans in series. Now, in parallel operation of the fans, the useful form, which is a very useful form of the capacity control. They can additionally equipped with the dampers, variable inlet vanes, variable pitch blades, and the speed controls to provide the high degree of flexibility and reliability. Means all the above four parameters can be included in the parallel series. The parallel operations is defined and having two or more fans blowing together side by side. So once we require the less volume, you can switch off the one fan. So the volume will be becomes half. Suppose two fans are working over there, then it becomes half. Pressure remains same. Okay, pressure will not be affected. So the performance of the two fans in parallel will result in double the volume flow rate. However, but only at free delivery. Whatsoever the free delivery is at that time, the double the volume rate will be there. The parallel performance curves, the higher the system resistance, less increase in the flow results with the parallel flow operations. So you can see the area, this curved area, where that you can operate the with a low resistance and the double parallel flows. However, if you go with a two series, however, if you go with a series, then multiple flanks, then push-pulley arrangement is considered, and the static pressure capability at a given airfoil can be increased. So this high pressure curve will show that the static resistance or static pressure will be goes on increasing. And in series operations, the best results are achieved in systems with high resistance. So best results, if we want to achieve, we have to give the high resistance. We have to overcome the high resistance. So whenever we go with this arrangement, they have mentioned that when we have to you consider this series combination and parallel combination, they mention over here that both series and parallel operations, which are particular with the multiple fans, certain areas of combined performance curves will be unstable and should be avoided. Okay. And this is the instability of unpredicted and is function of the fan and motor construction and operating points. They mentioned that over here that the series operation is best result are achieved in the systems with where the resistance is high to the gases or fluids, and the parallel flow is considered where curves are considered where the less increase in flow results with parallel operation, or where less resistance is considered, low resistance is for the gas flow or fluid flow. So we can operate parallel systems in less resistance area and series systems in high resistance area. Next point is the factors to be considered for the selection of flow control methods. So they have given few considerations for this one. There is a figure, here is it, and they have compared the 3 flow control strategies. The first strategy is the damper. This first one is the damper. I will write as A. Then second is the variable guide vanes, which is I will write as B. And third is the adjustable speed drives, that is the C. Now, as we go with the A, that is damper, they mentioned that even though the flow control is there up to 30%, if you control the flow, the power is only reduced up to the 50%. However, if you go with the variable drives, the power will be reduces up to 30 to 35%. And if you go with the adjustable speed drives, the power will be almost reduced to the 0 or up to the 5 to 7%. So among them, the adjustable speed drives are more efficient. Now, why this is happening? The reasons they have mentioned that if you go with the dampers, even though we close the dampers, there will be a leakages or slips of the air from the dampers. So there will be a power required to overcome that one. So the 50% only energy will be saved. The variable guide vanes also not fully closed. So almost 30% power is required. However, the speed, if you reduce with the change of pulley, then you can achieve a lowest. It cannot be 0, but it can be reduced up to 5 to 7%. Now, this control mechanism, they have mentioned 3-4 points. I'll highlight that points so that in figure text, they have mentioned some points which are which we have to note while studying the fans and blowers. First point, they have mentioned that when you go for the control, we have to consider the turn down ratio. Now, what is meant by turn down ratio? Is the ratio of maximum to minimum flow rate. So minimum flow rate is not always 0. So we have to reduce it. Then that maximum to minimum flow rate we have to consider. Then we can control the capacity. Then we have to find out the amount of leakages, that is slips, through the control elements. Like just discussed that the dampers have, even though we have closed the full dampers, there is a leakage. Then they have mentioned full closed may not be 0 due to the leakage through the dampers. If you go with the variable speed drives, the turn down ratio is limited by the control systems. So it cannot be 0. And in many cases, the minimum possible flow will be determined by the characteristics of the fan itself. So the stable operation of the fan requires that it operates in a region where the system curves have a positive slope and a fan curve has a negative slope. So I think in these factors to be considered, the most notable point which we should have is that whenever there is a curve we draw, the stable operation curve, that time we have to consider the system curve should be positive slope and the fan curve should have a negative slope. Again, they mentioned that the outlet damper control, due to its simplicity and ease of the operations and low investment cost, is most prevalent form of capacity control. However, it is the most inefficient of all methods because we are only controlling the flow. Our motor consuming the electricity are on the same capacity. So for the best suited situations, only small and infrequent changes are required. for example, minor process variation due to the seasonal changes, and then we can achieve economic advantages over the flow control. So that economic advantages they have considered with this help of different operating points. So the one method over the other determined by the time duration, that is how much duration we can control it, and over which the fan operates at different operating points. So these are the things which are covered under the factors which we have to consider for the selection of flow control methods. Now the next point, which is more related to the performance, that we have to assess the fan, that is fan performance assessment. We when go with a assessment, we have to find or measure the flow, we have to measure the head, and we have to measure the temperature on the fan side. Okay, and we have to find out the power rating input on the motor side. Now if you go with the flow measurement, what we have to measure, we have to measure the three factors. One is the static pressure. What is the static pressure? The static pressure is the potential energy put into the system by the fan. And here you can see one manometer which will connect it to the pipe, and the static pressure is mentioned, which is in mm of Hg or mm of water column. So whatsoever. The second point is the velocity pressure. Here they have mentioned the velocity pressure. Just a minute. The second point is the velocity pressure is the along the line of the flow. So you can see over here a second, yes, over here they have kept the velocity point, right? So this velocity pressure is along the line of the flow, and which is cannot be calculated directly, which is the subtraction of total pressure and the static pressure. So results from the air flowing through the duct, this velocity pressure is used to calculate the air velocity. So they have mentioned the equation for this channel. I will go that equation and again I will come back to this one. Yes, this one. So the total pressure is the summation of static and velocity pressure. In previous diagram, we have seen that there is a difference between TP and SP we have to calculate, and that inserted into the tube. The velocity pressure and the static pressure can change as the air flow through the different size duct. So the diameter of the duct varies, the static and velocity pressure can be changes. Okay, however, the total pressure remains constant. It will changes with the friction losses. So this is related to the static pressure, velocity pressure, and the total pressure. In this segment, the few things which we have to note that this fan flow is measured with the help of a pitot tube and manometer combination. Sometimes they are used with a flow sensor, that is differential pressure instruments, or with an accurate anemometer. So three instruments we can use to measure the fan flow. One is the pitot tube with manometer combination. Second is the flow sensors with differential pressure instrument, and third is the accurate anemometer. But what the care we have to needs to be taken regarding the number of transverse points, number of points we have to take, and straight line length section, so that the turbulence flow regions can be avoided. Okay, it will give a errors in our management. So we have to consider the straight line section upstream and downstream of the measured locations. So different measuring locations we have to consider, and we have to measure this flow at suction and discharge sides, and preferably on the both sides. So both sides will give us the accurate result. Here they mentioned one instrument, that is pitot tube, how we can measure the pressure flow. So measurement by pitot tube. In this measurement, there is a airflow inside the duct, and along this pitot tube, which is 90°, the one portion is considered connected to the manometer, which will give us a total pressure, and another point is connected at this point, which will give us the static pressure, and difference of these two is the velocity pressure. So velocity pressure is measured using a pitot tube and a manometer. When the inner and outer tubes ends are connected to a manometer, we can easily get the velocity pressure. Here they also mentioned that for going for the low pressure measurements, we have to go with the inclined tube manometer instead of the U2 manometer. So these are the suggestions which they have put in this chapter. The next point, how we have to measure and calculate. First, we have to measure the velocity points, velocity pressure, and the velocity. Here is one duct, its cross-sectional area they have taken, and they have mentioned different points. This is a 0.974 diam. This is that a 0.774 diam. So different points are there, and over that points, we have to measure the pressure, velocity pressure. The few things they have mentioned over here, that we have to take number of points, one thing, okay, and we have to try to avoid to measure at the circumference of the or inside the tube, just inside the tube surface, because the layers at inside the tube are mostly resistive, so the accuracy of the velocity pressures are restricted. The velocity pressures varies across the duct, and the friction slows the air near the duct walls. So velocity is greater in the center of the duct. So we have to measure these velocities. Okay. The velocity is affected by the changes in ducting configuration, such as bends and curves. We have to take the measurements in section of the duct, that is straight line. That is a straight line, and we have to take at least 3-4 diameters after any elbows or branch entries or duct size changes. We have to take the measurements. Here they mentioned that we have to determine the average velocity, and from that average velocity we have to go for the predictions. They mentioned that don't go with the average pressure, because pitot tube will give the average. Don't go with this average 1, 2, 3 and divided by number of calculations. They said that for this pressure, calculate velocity. For this pressure, calculate velocity. For this pressure, calculate velocity. And all the velocities you have to take the average of that system, average of the system. So they mention over in next point that we have to calculate, we should calculate the velocity of each velocity pressure reading, and then we have to go for the average of the velocities. Do not average the velocity pressures which we have measured from the pitot tube. Measure, do the average of the velocities, not velocity pressure, but the velocities. Also, they have mentioned that whenever you go for the measurement, take one set of readings along that one direction and another on the 90-degree angle to the first. So the two different measurements we have to take. Then if you go with a square duct, this is for the cylindrical filter. If you go with a square duct, the readings can be taken at 16 equal spaced areas. And if it is not possible, take the approximate average velocity, which can be calculated by measuring the velocity pressure at the center of the duct, and then we have to calculate. So at the center of the duct, we have to take the 6 velocities. All the 6 velocities we have to convert it to the average. We have to convert to the velocity. Sorry, 6 velocity pressures we have to calculate, measure, not calculate, measure, and then for each velocity pressure we have to calculate velocities. All these 16 velocities, then we have to take the average. They also mentioned that the value is reduced to the approximate average and is multiplied by 0.9. Here they have mentioned, I will show that one. They mentioned that only we will go, not only go with the averaging, that is we have taken the 16 static pressure, then calculated the 16 velocities, then summation of 16 velocities divided by 16, that will not be gives a proper result. What we have to do, we have to multiply them with a factor that is called 0.9. This is they have mentioned. We have to multiply that 16 equal space areas, find the static velocity pressure, from that velocity pressure to velocities, and then multiply by 0.9. Then how to calculate the velocity? They have mentioned over here. The calculation of velocity, the formulas are over here. The velocity, that is meter per second, is equal to Cp, and Cp stands for pitot tube coefficient. That is given by the manufacturer, or we have to assume it is by 0.85. Then the delta P, that is average velocity pressure, which is measured using the pitot tube and inclined manometer by taking number of points over the entire cross-sectional area duct. Its value is mm of water column, and gamma is the density, gas density at flow conditions, whose unit is kg per meter. So this becomes the equation for the velocity, Cp into under square root 2 into 9.81 delta P divided by rho. So we have to take the product of all these threes, and then we have to take the square root, and then we have to multiply it with the Cp. A simple example also they have put over here. The example is the airflow measurements using the pitot tube. Hello, am I audible?
Yes, you are audible.
Okay. Yes, thank you. A simple example they have taken. There is an airflow measurement using a pitot tube in the primary air fan of a coal-fired boiler gave the following data. Calculate the velocity of the air. The temperature they have given, air temperature is 38 degrees centigrade. The velocity pressure is 47 mm of water column. Pitot tube constant, Cp is 0.9, and the air density is at 38 degrees centigrade, that is 1.135 kg per meter cube. So once we add the values, the value becomes 25.6 meter per second. Also, there is a second point, that is the gas density. They have given the equation density rho is equal to kg per meter cube, P into M divided by RT. P is the absolute gas pressure, mm of water column. M is the molecular weight of gas, kg per kg mole of, that is in case of air, M is 28.92 kg per kg of mole. T is the gas temperature in Kelvin, and R is the gas constant, which is 847.84 mm of water column meter cube per kg mole Kelvin. They mentioned that whenever there is a calculation for the molecular weight, we have for the different gas constituents like CO2, CO, O2, N2, like that, on the dry basis, kg per kg mole, you have to take the percentage CO2 and its molecular mass, percentage O2 and its molecular mass, percentage CO and its molecular mass, percentage nitrogen and its molecular mass, divided by. You can calculate the volume calculation, that is volume in the duct, volume of flow, Q meter cube per second is the velocity, V meter per second into the area. Now the two efficiencies they have mentioned over here, which need to be considered because that efficiency are more important as far as the energy conservation point of view. The fan manufacturers generally uses the two ways to mention fan efficiencies. One is the mechanical efficiency, sometimes it's called as the total efficiency, and the second one is the static efficiency. The both measure how well the fan converts the horsepower into flow and pressure. So the fan mechanical efficiency is in percentage is given by volume in meter cube per second into delta P, that is total pressure in mm of water column, divided by 102 into power input to fan shaft in kilowatt. Secondly, the static efficiency equation is the same exact that of the output velocity pressure, which is not added to the fan statics pressure. So only difference is that here the total pressure is considered, and in second static pressure is considered. Remaining equation is same, that is volume into delta P divided by 102 into power. So delta P if taken total pressure, or delta P is taken static pressure. Now the few things are there, that is energy saving opportunities that we have to consider, that we have to minimize the excess air level in combustion systems to reduce FD fan and ID fan load, then minimize the air in leaks in hot flue gases path to reduce ID fan load, especially in case of planes, boiler plant, furnaces, etc. In cold air leaks, increase the ID fan load tremendously because of the density increase in flue gases, and in fact it choke up the capacity of the fan, which will result in the bottleneck of the boiler itself. Then third is the in-leak and out-leak in the air conditioning systems also have a major impact on energy efficiency and fan power consumptions, and that need to be minimized. A few findings of the performances are there. We have to change the impeller by high efficiency impeller. We have to change the fan assembly as a whole by higher efficiency. Impeller derating, change the metallic or glass reinforced plastic with the FRP impeller. Fan speed should be reduced. Then option of 2-speed motors or variable speed drives are more useful in variable duty conditions. Then option of energy efficient flat belts or cogged raw edge V belts in place of conventional V bends is adopted. Then adopt the inlet gate vanes in place of discharge damper control and minimize the system resistance and pressure drops by improvements in duct systems. Now there is one case study they have taken. Okay, sir, is it up to 5 p.m. or 5:30 p.m.?
I think
Okay.
5:15. No?
Okay, till you can say, yeah, till you can say I will continue, and whatever will be remain, I will cover in the tomorrow. Tomorrow also one
I
session
think
we can have.
Batul sir had joined.
Sir, Harshad here. If you want to continue, you want to finish the lecture, you can finish it. Later on, I'll start my lecture.
Yes, sir. Yes, sir. Just give me 10 to 15 minutes, sir. Thank you.
Okay, sir. Okay, sir. No problem. Thank you.
Thank you, sir. Now there is a simple case study of the pressure drop reduction. There is a problem arises for the back filters for a cement mill. What the problem they arises that there is a high pressure drop which across the bag houses while producing one particular type of cement product. What are the reasons they have find out that there is a characterization of a particular size of distributed association with its finesse is creating high drop pressure or differential pressure across the bag houses. So different sizes of the particles of the cement will creating this one. So what will be the solution? They have just applied one simple solution that replacing the existing filter bags with PTFE, that is polytetrafluoroethylene membrane bags, filter bags. They also mention here that what will be the result. That is the excellent one. That the reduction of the 50 mm water column differential pressure across the bag house, and there is a reduction of 5 kilowatt hour in power consumption. So they mention over here the parameter that existing bags and bag with membrane, their gas flow, their temperatures, then what are the material used. The interesting part is the DP, that is differential pressure across that one. Initially, it was a 165 mm of water column, and right now it drops to the 115 mm of water column. The consumption also reduced from 51 to 46 kilowatt. So what are the conclusions they have mentioned? That our results can categorically demonstrated that by changing a filter fabric can achieve significant performance improvement of the bag house. So like that, the different case studies they have mentioned, these are the slide one, is what will be the VSD. So they have mentioned the case studies of 1, 2, and 3 and 4. They have mentioned that the reduction in power consumptions, if you go with a high capacity fans with a variable speed drives fans, then they shown that the last one is the simple measure results in the 53% reduction in power consumption, which amounted annual saving of 2.1 million. So in cement industries, how we can go with this achievements that uh, clinker cooler and the cement plant shows that flow was much higher than the required. So the old state blade impellers result is there's low efficiency. So instead of old state blades, they will go with a backward curve blades. So this will increases the performance of the fan, and that increased performance is measure the 53% reduction in power consumption. And if you compare with the cost, it becomes 21 million savings observed by them. Like that, the different case studies they have, we will not go into that one. Okay, you just go read that one, how the simple one. I just want to point out one things. As you are in industry, you have used it. Have you heard about the CFDs and the softwares used for the CFDs? Sir, anyone can tell that, have you come across with a computational fluid dynamics or the CFDs? The CFDs are considered for the variation of the fluid flows. I also come across with this new concept which they have measured. Normally, in academics, the computational fluid dynamics are considered for the fluid flows for the heat transfers or the combustion related parameters. But first time I have just seen that how the CFD is used for the energy efficiency. Just take one look over here. This is the older design, okay, of a one factory, okay, where the industrial draft flow, which has a double intake fan, has been considered. So this is the diagram or a system which will have a induced draft fans. Their CFD model has been created, and that CFD model with the nodes and everything has been used to analysis. And this is the good analysis they have marked over here, that the black circles, these are the black circles or ovals, shows that the flow get distracted and there becomes a turbulence increase over there. Also, there is a white circle over here where there is an extended portion which is of the no use. So they modified in this new one, that is figure 5.23, that then they have done the CFD analysis, and that shows that the flow will becomes reducible, and that reduced flow will increase the efficiency of the system. That efficiency is almost that pressure drop is increased from decreased from 251 Pascal to the 66 Pascal, and that will use the 49 kilowatt saving for the system. So such type of systems we can analyze with the help of the CFDs, because sometimes we cannot go with each time the experimental work. So for that, these CFD systems are more helpful to design or to predict the corrections for the existing designs. The last point, which is related to this one, is the one case study they have considered. A V-belt centrifugal pump is supplied air to a process plant, and the performance test on the fan gave the following parameters. They have given the air density, ambient temperature, the diameter, velocity pressure measured by pitot tube in discharge duct, then the pitot tube coefficient, then static pressure at fan inlet, then static pressure at fan outlet, then power drawn by the motor coupled with a fan, then belt transmission efficiency, and the motor efficiency at a operating load. So these are the parameters given. Few parameters they have mentioned over here. With the help of these parameters, first they have calculated the area of the duct. They have calculated the area of the duct, this one. The 3.14, that is the length, pi, then r is the point, and diameter is there, pi d square by 4. So d 2 times 0.8, this is the pi, and divided by 4. So this is the area they have calculated. Then they have calculated the corrected gas density, that is 273 into 1.293. 1.293 is the density of the air multiplied by its temperature. This 1.293 density is at 0 degree centigrade, but our system is at 40 degrees centigrade. So temperature into density divided by the 0 temperature and 40. This is like that. A stands for B. Then what will be the value of the X if it becomes, what will be the value if it becomes X? So that for 0, the 1.293 is the density. What for the 40 degree? We have to cross multiply and the find out. That becomes 1.1277. Then with the equation which I have mentioned, we have to find out the volume, which becomes 12.65 meter cube per second. Then the power output of the shaft, we have to calculate. This power output of the shaft, they have calculated, they have mentioned the power output, that is 75 kilowatt. However, in the example, they also mentioned here that there is two efficiencies, that is belt transmission efficiency and motor efficiency. Both we have to consider, right? So that two efficiencies, when we measure, multiply it, then 75 into 97 and 93. So here, where is it? Yes, here. So power input is 75 into 97 into 93. So it becomes 67.65. Then we have to find out the static efficiency. That efficiency, static fan efficiency, again volume, total static pressure difference, 102 into power output. Now the volume we have calculated here, that is the 1265 we have consider here. Then static difference, here they have mentioned 185 mm of water column minus the static pressure at inlet, that is minus 20. So minus plus, multiply by 12.61 divided by 102, and this is the power output we have taken, static power output 67.16. Then the fan static efficiency becomes 37.58%. So this will be the static efficiency with the help of a numericals. In this chapter, they have only mentioned the simple numericals and the what you can say, its values. Okay, so these numericals we have covered. If you have any questions, please feel free to ask. Suresh sir.
Yeah, okay, sir. You can continue. I mean, I don't have any question.
Yes. Then can we go for the last one? That is the MCQs, as
Yeah,
everyone
yeah.
has taken. Yes. Then first one, in a textile mill. In a textile mill, two 150 CFM belts driven reciprocating compressors are seen to be working constantly with a load time of 20 seconds and unloading time of 30 seconds. The best economic option for the energy savings would be switch off one compressor and reduce motor pulley size of the another compressor approximately. Third is the adopt variable speed drive for one of the compressors and none of the above. What do you think?
B, option B.
Why?
Because unloading time is more than 30 seconds, no? And actually the loading time is 20 seconds.
Yes.
So it is better to switch one compressor, and second compressor we can reduce the pulley so that we can get the best efficiency.
Yes, that is a good example. Okay, so the answer is B. Next, the specific ratio as defined by ASME and used in differential fans blowers, and compressors is given by A. Discharge pressure upon suction pressure, B. Suction pressure upon discharge pressure, C. Discharge pressure upon in bracket suction pressure plus discharge pressure, and D. Suction pressure divided by suction pressure plus discharge pressure.
Specific ratio, ये discharge pressure.
Discharge pressure upon suction pressure.
Suction pressure, right?
Yes. Then C. The efficiency of backward inclined fan compared with to the forward curves fans is
Higher. It is a
lower, higher. Yes.
Yes.
Fourth one, for centrifugal pumps, the relation between the shaft input power and speed is given by
That is cube of RPM. N1.
yes,
KW.
cube of RPM. Yes, KW1 upon KW2 is equal to N1 cube upon N2 cube. It is a cube. The power is related to the when it goes with the speed, it cube. Then yes,
parallel operation is double.
yes, power of operations is the double. And the third one is the single one, that is a discharge. Specific speed, pressure is the N1 square, and discharge is related with the speed. Then parallel operation of the two identical fans in a deducted system is
Parallel
will
operation,
double.
Yeah, it will double.
It will double the flow. Yes. 6 I have not calculated. You can calculate. I also calculated that one, and then we will come to this one. Okay.
Yes.
A fan of operating.
388.5. I have calculated.
388. Okay, 388.5. Yes, I will calculate and again come to that one. It's 388.5. Then identify the correct statement. The specific ratio of compressors is higher than blowers. B. Specific ratio of fans is higher than blowers. Specific ratio of compressors is lower than fans. The specific ratio of blowers is higher than compressors.
Yeah, compressor has highest higher
specific ratio. So it is a. Yes. 8. Decreasing the RPM of the fan at partial loading by 10% results in A. Decreasing of 10% in flow rate and decrease in 27% in power requirement. B. Decreasing of 10% in flow rate and decreasing of 19% in power requirement. C. Decrease of 10% in flow rate and increasing of 10% in power requirement. And D. Increasing 10% in flow rate and no appreciable change in power requirement.
It is the A actually. Decrease of 10%.
Yes, it is a. Yes, it is a 10% and 27%. It is mentioned over there.
Yes.
Now, the last point is the power drawn by the centrifugal fan is A. Inversely proportional to the fan efficiency. B. Directly proportional to the fan efficiency. C. Inversely proportional to the static pressure. And D. Inversely proportional to the flow rate.
Power drawn. Inversely proportional. Option A is correct.
Yes, A is the correct, because they have given it tricky. We have to find out the fan efficiency, and that we have to correlate with the that center power. So divided by 102 into power. So it is a fan efficiency. Either it is a static fan efficiency or total fan efficiency. It is inversely proportional to the power. Yes. And the last is 10th is the main reason for using variable frequency drive VFD for capacity control in electrical motor driven centrifugal fans with fluctuating load is A. Improved power quality. B. Fan capacity is proportional to its speed, whereas the power drawn by the fan is proportional to the cube of its speed. C. Improved power factor. And D. Precise closed loop process control.
Fan capacity.
Fan capacity B. Yes, fan capacity is the proportional to its speed, whereas the power drawn by the fan is proportional to its cube of its speed.
Speed cube of the speed.
Yes. Thank you. We will take the break and then
Okay.
So you can have like 5 minutes break, then we can start the lecture for pump and pumping system, because it will take another 2 hours to complete it.
Yeah, yeah. In 5 minutes we will meet, sir.
Yeah,
Just-
5:25 we'll start.
Okay, sir.
Yes, yes. Give-
Harshad sir. Hello. Hello.